Hi everybody. Today we're going to continue our discussion of viral ecology, and today focusing on viruses that infect humans. This is obviously a hot topic right now, and there are an infinite number of places you could go to learn more about human viruses. So for this video, I really just want to focus on a couple of things that I think are important for anybody to know about the very general topic of viruses infecting humans. So first, a couple of terms I want to define. The first one being emerging virus. This is just a virus that is causing a new disease that we hadn't previously recognized before. So a new disease pops up, and the virus that causes that disease we call an emerging virus. It's not necessarily a new virus to the world, although it certainly could be a virus that has evolved recently. It could also be a virus that's been around for a while that for some reason has suddenly caused a disease that is attracting human attention, right? New to human attention is not necessarily the same as new to the world, although a virus could be both new to the world and new to human attention. The second bullet point here is saying that emerging viruses are not new, meaning that the concept of viruses emerging is not new. Viruses have been emerging ever since the beginning of life. Most likely, the concept of a new virus appearing and causing a new infection is a fact of life in every sense of the term. That's just a part of biology. Viruses are always emerging. However, there are things that humans do, especially in the 20th and 21st centuries, that can make dramatic consequences of emerging viral infections to be particularly acute or particularly dramatic. And that's what we're going to talk about today. Is basically how human behavior can facilitate viral infections and guide the consequences of viral infections in particular ways, mostly as a result of human behavior, not so much because of viral biology, although obviously it's the interaction of the two, the viral biology and the human behavior. The other term is spillover event. A spillover event is when a virus jumps species, essentially. So a virus is infecting a species, and for some reason something causes it to overcome some kind of biological or geographic or other barrier to start infecting a different species than it was infecting before. That's called a spillover event. Okay. In my last lecture, I talked about the concept of kill the winner, which is how viruses can have a stabilizing effect on ecosystems by infecting the most abundant population in an ecosystem. So the more abundant you are, the more susceptible you are to a viral infection. And the consequence of that is that there's a huge cost to becoming super abundant and potentially making an ecosystem unhealthy. And in that way, viruses can have a beneficial impact overall on ecosystems. And right now, humans are the winners, and therefore humans are being killed by viruses. We are more and more likely to suffer massive viral infections the more of us we are, especially living in dense population clusters in cities. We will always have viral infections as long as we live in cities. That has always been true ever since we started living in cities, and the bigger and bigger our cities get, the more massive the viral infections will be. That is just a fundamental law of biology. The denser your population is, the more viral infections you're going to have. That's how it works. That's what we talked about in the previous lecture with the kill the winner ecological concept, and that's exactly what we're experiencing right now, is the kill the winner effect. Not only our population, though, various aspects of our global society and culture can make viral infections to be more likely or to spread faster. Mostly is what we're doing is that we're making it very easy for a single viral strain to instantly be transmitted all over the world, which is a pretty new thing that's really only happened in the past couple of decades. So that is a really big new thing that we're doing as a species and in the world. And these are just some of the many ways that we facilitate viral infections as part of our society. Globalism is a very simple but accurate way to describe it. Okay, so now a little bit more about the biology of spillover events and emerging viruses. So this is not the only way to talk about this concept. These are not the only terms one could use, but here's one example of how you could think about it. A stable system is when a virus is infecting a given species in an ecosystem, and it's kind of at an equilibrium. The species is not going extinct. The virus is has a healthy population. It's in equilibrium, right? You could say everyone's happy, except those probably few individuals who are infected by the virus. So an evolving host-virus interaction is when the virus is exposed to a naive population. So it could be a subpopulation within the same species that hasn't been exposed to that virus before for some reason, which could be a geographic barrier being overcome, or it could be a biological barrier being overcome, like a receptor binding change in the virus or in the host biology, or it could be jumping to a new species. So it's similar biology in either case. Evolving is a somewhat unfortunate choice of term because a virus is always evolving biologically, according to Darwinian evolution by natural selection. This use of the word evolving means that the nature of the relationship between the host and virus is changing over time, so it's using that sense of the word evolving, not biological evolution, because viruses are always evolving biologically. So a dead end is when a virus jumps to a population or to a different species and it doesn't go anywhere after that. It's a dead end one way. It's not able to jump to another species after that. And for whatever reason, the biology of that interaction with the new species is such that it also doesn't transmit very much within that species. This is really common, as we'll see on the next slide. And then there's the resistant host possibility, where it's similar to the dead end situation, except that the infection is just blocked. So those individuals in that population, for some reason, just prevent the virus from infecting them at all. And so it's not really a dead end. A dead end is when the virus is able to infect the individuals, and there could be a lot of death in the individuals of that species. But the virus doesn't go anywhere after that, where in this case, the individuals are mostly healthy. They are not affected by the viral infection. And then in both these cases, the dead end and the resistant possibility, it's possible if there's a change in the biology or maybe even something else, it can go back to this a changing relationship and then maybe even go back to stable, right? So these, even though this is called dead end, it's possible if something changes, it could go to a different relationship, but something would have to change. Okay, I think these examples are maybe even a better way to talk about essentially these same concepts. In here we have 5 different stages rather than the breakdown in the previous slide, and it has some really good examples. So example 1, there's a pathogen in animals, but it's never been detected in humans. Okay, so there's an example of that. And all these are focusing on the spillover case, where the virus goes from some other animal species to humans. So the second example, rabies, is a great example where there are cases where the pathogen can jump from the animal species to humans, but then it doesn't transmit among humans. So rabies is a great example because occasionally people get infected because of some kind of encounter with another animal, but humans don't transmit rabies among each other. Humans can die from rabies, right? This is still a serious disease, but it's not a human-to-human infection dynamic. Ebola on this diagram is described as being stage 3 because it can be transmitted between humans, but it doesn't stay as a human disease very long. So it's mostly a disease that has a reservoir in some other animal species, for example, bats, and it can be transmitted to humans. And it can be transmitted human to human. Ebola can be transmitted human to human, which is how you get Ebola outbreaks. But the Ebola outbreak among humans never lasts very long. So it can be extremely deadly, very sad and very tragic, right? We don't want to minimize it because Ebola is so deadly. But it tends to die out more or less on its own. Of course, we always try to limit the spread of Ebola, and there's nothing to say that it's not possible for Ebola to spread all around the world, right? So we should always treat every Ebola outbreak as a serious thing to be contained. But so far, all of the examples we have so far, the Ebola outbreaks die out, and I don't think we actually know why, right? There are some ideas out there about why it happens. Part of the idea is that it's so deadly that it kind of kills its human victims too quickly to maintain a transmission network. But I actually don't think that is completely settled as a research question. And in part because Ebola is so rare, and because it occurs in parts of the world where there isn't much science funding, we actually know surprisingly little about Ebola. I encourage you to read more if that intrigues you. Stage 4 example here is dengue fever. So in dengue, there is transmission from other animal species to humans, for example, monkeys, and then there's transmission between humans and humans, and that human-to-human transmission can be sustained. So you can have prolonged outbreaks of dengue among human populations, within human populations. And then stage 5 is when it becomes entirely human. So HIV evolved multiple times independently, actually. There are multiple strains of HIV that each independently evolved from the simian immunodeficiency virus, so the virus that infects monkeys and gorillas. And now it is an entirely human virus, HIV, that is entirely sustained by transmission among humans. And unlike dengue, the continued cycle of transmission does not depend on repeated spillover events from another animal species. HIV is pretty much here to stay without any additional contact with other animals. Okay, so this would also describe probably all human viruses. It seems like all human viruses must have evolved from some other virus that was infecting other animals, going all the way back to the origin of our species. So how common are these spillover events? Extremely common for viruses to jump species and then basically nothing happens. So the dead-end scenarios are thought to be extremely common, like rabies. As being just one example, humans can very frequently become infected by a virus that is normally present in another species. Now, for that to sustain a whole transmission network, that is very rare. It's common enough that it affects us greatly when it does happen. It seems to be happening these days at least once a decade, if not once every few years. It could become more common. But among all of the spillover events that must happen constantly every day, or probably multiple times a day, those big outbreak events are relatively rare. Because they are so rare, you can never predict them. You can't say when a spillover event is going to occur. We can identify particular types of viruses and areas of the world that are more likely, where we have all of the preconditions for a spillover event to occur, as we have several examples of those things happening, and there are some common properties among them, which I'll talk about on the next slide. So all we can really do is monitor and sample wild animals known to be reservoirs of human viruses or viruses that are potentially capable of jumping to viruses. Direct science funding to those areas of the world where we know spillover events can occur, but we can never predict. We can never tell. We can never say exactly the event is going to occur at this time and at this place with this virus. You can be prepared, and the way we can be prepared is to learn the lessons of the past. So you may have heard in 2003 there was a very deadly global outbreak of SARS, which is a coronavirus. This was SARS-1. We are currently living through SARS-2. It is SARS-CoV-2 is named after this SARS that occurred in late 2002 and 2003 because they are genetically very similar. So this is a story about the first SARS outbreak. It also started in China. Was characterized as a severe pneumonia. So it led to really bad illness. Although it did have a relatively long incubation period, which is similar to SARS-CoV-2. They differ in some other details of the incubation period, but a relatively long multi-day incubation period is a shared feature of both SARS-1 and SARS-2. This is how SARS-1 was able to spread so widely around the world because of this incubation period. But the difference with SARS-1 is that once people, there was a much higher rate of developing serious illness and death with SARS-1. The two events that contributed to the rapid and global spread was that it happened right around the Chinese New Year. So there were millions of people in China who were traveling around the world. It's traditional for the migrant workers who are generally working in cities unofficially and undocumented to go back to their home regions at the Chinese New Year. So you had this spread from big cities out into the rural areas that made it hard to control. And then there was this famous event of a doctor who had been treating infected patients who went to a hotel in Hong Kong. And Hong Kong, of course, is a very cosmopolitan city where lots of business people are traveling in and out. And this was kind of case zero for spreading SARS all over the world. So this is how it got out of China. And we know this because there was a huge investigation into what led to the global outbreak of SARS. And there was an amazing number of resources that went into the investigating exactly how this happened, involving very thorough sampling of this one particular hotel. And you should look up the story. It's a really good kind of whodunit mystery investigative story that came with a very definitive answer. Similar things are going on with SARS-CoV-2, but it's a bit more complicated. So, trying to limit myself to SARS-1 for right now. So here's a little bit more about the hotel story. In the hotel, at least a dozen guests were infected from the hotel. They were able to determine that's a dozen people they have like very firm evidence actually contracted it at the hotel. There must have been many more than that. And then from there, they went all around the world. And again, this incubation period that's symptom-free, this asymptomatic incubation period, which we also have with SARS-CoV-2, is what allowed the global spread. So 10% mortality with SARS, which is much, much higher than SARS-CoV-2. And luckily, it just suddenly stopped one day. It's still a mystery why SARS-1 basically just suddenly disappeared. There are lots of ideas out there, but my understanding is it's still mostly a research mystery. Part of it might be because of the high mortality, that so many patients were dying, that self-limited the spread. But again, that's not a settled question, I think. It's still kind of mysterious and perhaps very, very lucky that SARS stopped when it did. So where did SARS come from? So it's certainly a spillover event. SARS-like viruses have been identified in lots of bats, especially in China. In Hubei province, 70% of the bat species had antibodies against SARS. So it's not even a single bat species, but many bat species that have SARS-like viruses. However, we don't know exactly the transmission pathway. So the human SARS coronavirus is very similar to coronaviruses, multiple kinds of coronaviruses that have been identified in multiple bat species, but they're not identical, and they're different enough that makes many people wonder if there was some secondary host, some host in between the bat and humans, and the palm civet cat, which is a very strange mammal you should read about, was perhaps the intermediate host, that somehow a palm civet cat contracted a coronavirus from a bat, and then palm civet cats, which are also known to be sold at the meat market, were then transmitted to humans. It was transmitted to humans from there, perhaps because of interaction with the animals at the meat markets. Again, this is often presented as established fact that SARS-1 came from palm civet cats as a stepping stone from bats, but this is actually not a completely settled question. I think there's general agreement that there must have been some kind of intermediate host because the distance from the bat virus to the human virus is so great, but I think there's still some uncertainty about exactly which host there was, and maybe alternative possibilities as well, like maybe some undiscovered bat species that does have viruses that are much more similar to the original SARS. This is also an option. I want to mention that SARS is not the only coronavirus that has known animal hosts. So this is a really great review on multiple coronaviruses and their origins, published in 2018. So this is before the SARS-CoV-2 COVID-19 outbreak. And I like to show this figure to point out that before the current pandemic, we already knew of multiple human coronaviruses that each came from animal hosts. So a lot of these now cause basically common colds. They don't cause serious illness. But when they first jumped to humans, which might have been 100 years ago, multiple hundreds of years ago, maybe thousands of years ago, maybe they did cause a pandemic, and those events have been lost to history. There are a couple of events that people have found in history where there was some kind of big flu outbreak, and people have speculated that maybe some of those were caused by these coronaviruses that are now endemic to humans, and now they just cause common colds in humans. A lot of those are speculative, but there are some intriguing ones. But the point is that we already knew years ago that coronaviruses are constantly jumping from lots of different animal species: bats, mice, cows, camels, civet cats, perhaps, pigs. This is actually a llama, I guess. The camel one is very well established. This was an outbreak just a few years ago, I believe, in the Middle East, where the researchers were able to very definitively show that this MERS coronavirus originated in bats, was somehow transmitted to camels, and then humans picked it up from camels. Luckily, this was another example of an outbreak that ended very quickly. A bunch of people died, but then the infection network fizzled out, and I think still, again, mysteriously, the outbreak just stopped and disappeared. So again, I think we're probably lucky here that this MERS outbreak didn't last very long. SARS still killed a lot of people, but it didn't kill the millions that it's killing with SARS-CoV-2. And so we've been lucky multiple times in just the past few years. And then finally, we were not so lucky with this one, I guess, is the main point with this. Okay, so this raises the question, where did SARS-CoV-2 come from, the one that we're currently dealing with? And this is one of the really early papers that came out in the early days of the pandemic, in red showing the first few samples of SARS-CoV-2. You see the sample dates from 2019, so this was some of the very first patients with documented SARS-CoV-2. And in this tree, they are very closely related to this bat virus, which is now famously known as RATG13. And there's this clade of SARS-CoV-2 that includes both human and bat viruses, very closely but clearly distinct from SARS-1. And here are those bat and civet cat and human SARS-1 viruses. So here's the human SARS-1 virus, very similar to the civet cat virus, which is why that theory has a lot of support. And then the similar but distinct bat SARS-1 viruses. So here's one SARS-2 virus from a bat, and then the human viruses. So again, this is very similar, but in the future we will look at papers that look at this relationship even more closely and see that there's still quite a bit of distance, even though it doesn't look like it on this particular tree, between the bat virus and the human virus. So in SARS-CoV-2 as well, there is still some question about whether there might have been some intermediate host between bats and humans. Okay, that question still does not have a definitive answer today, and it's something that we can read and discuss more about in our class. And that is, in fact, what we'll do next time, and I'll see you then. Bye-bye.